Welcome to this video on Quadrix numbers. If you've ever wondered about numbers that go beyond the complex plane or even quaternions, you're in the right place. Today, we're diving into Quadrix numbers, a fascinating four-dimensional number system that encodes 2x2 matrices in a purely algebraic way. So let's get started. What are Quadrix numbers? Let's start with the big picture. Quadrix numbers are a four-dimensional number system built on four fundamental building blocks, I, J, K, and R. The main idea behind them? To represent 2x2 matrices in a simple algebraic way, making operations like multiplication or finding square roots much cleaner than traditional matrix methods. To understand where Quadrix numbers fit in, let's compare them to other number systems. Complex numbers like z equals a plus b times a are 2D with I squared equal to -1. Quaternions like q equals a plus b times I plus c times j plus d times k are 4D with I squared, j squared, and k squared all equal to -1. Quadrix numbers are also 4D, but their basis elements follow different rules. I squared equals I, R squared equals R, while j squared and k squared both equal 0. These unique properties make Quadrix numbers perfect for encoding 2x2 matrices, as we'll see soon. A general Quadrix number m is written as m equals a times I plus b times j plus c times k plus d times r. Here, a, b, c, and d are coefficients. They can be real numbers, complex numbers, or even functions. But their real job is to scale the four basis elements, I, j, k, and r. This form isn't just abstract, it directly corresponds to a 2x2 matrix. Specifically, M maps to the matrix with A and D on the diagonal and B and C off the diagonal. To see why, let's define the basis elements as actual matrices. I is the matrix with a 1 in the top left corner and zeros everywhere else. J is the matrix with a 1 in the top right corner and zeros elsewhere. K is the matrix with a 1 in the bottom left corner and zeros elsewhere. R is the matrix with a 1 in the bottom right corner and zeros elsewhere. When we write M as a combination of these basis elements, it expands into the full 2x2 matrix form. For example, a times I plus B times J plus C times K plus D times R becomes a matrix with A in the top left, B in the top right, C in the bottom left, and D in the bottom right. Now let's explore the algebraic rules that make Quadrix numbers special. First, the squares of the basis elements behave in unique ways. I squared equals I, R squared equals R, J squared equals 0, K squared equals 0. This means I and R are idempotent, squaring them gives back the original element, while J and K are nilpotent, meaning squaring them results in 0. These rules hint at a non-commutative system, since matrix multiplication isn't commutative. Let's test this by multiplying I and j in both orders. First, I times j equals j. But if we reverse the order, j times I equals 0. Since these two results aren't the same, Quadrix numbers are indeed non-commutative, just like matrix multiplication. Another crucial property is the identity element. For Quadrix numbers, the identity is I plus r. Why? Because when we multiply any Quadrix number by I plus r, we get back the original number. This matches the 2x2 identity matrix, which has 1s on the diagonal and 0s elsewhere. To confirm, let's expand the multiplication of a general Quadrix number m with I plus r. After applying the basis rules, we see that all terms simplify back to m, proving that I plus r truly acts as the identity. Multiplication table defines how basis elements multiply with each other. We already know the squares, but we need the cross terms, like I times j, j times k, and so on. There are 16 possible products, I, j, k, r times each other, and we'll derive each using matrix multiplication to ensure accuracy. Let's compute them systematically. First, I times I equals I, j times j equals 0, k times k equals 0, r times r equals r, I times j equals j. Now j times I, so j times I equals 0. Notice I times j does not equal j times I, confirming non-commutativity. Next, I times k, so I times k equals 0. For k times I, so k times I equals k. Now I times r, so I times r equals 0. For r times I, so r times I equals 0. Next, j times k, so j times k equals I. For k times j, so k times j equals r. Now j times r, so j times r equals j. For r times j, so r times j equals 0. Next, k times r, so k times r equals 0. Finally, r times k, so r times k equals k. Here's the complete multiplication table. Notice the non-commutativity, j times k equals I, but k times j equals r. This table is the backbone of Quadrix algebra, guiding all multiplications. Let's use it to multiply general Quadrix numbers. Now let's multiply two general Quadrix numbers. m equals a times I plus b times j plus c times k plus d times r, and n equals e times I plus f times j plus g times k plus h times r. We compute m times n equals a times I plus b times j plus c times k plus d times r times e times I plus f times j plus g times k plus h times r. Distribute each term using the multiplication table to simplify. Collect terms, I terms, ae times I plus bg times I equals ae plus bg times I. J terms, af times j plus bh times j equals af plus bh times j. K terms, ce times k plus dg times k equals ce plus dg times k. R terms, cf times r plus dh times r equals cf plus dh times r. So m times n equals ae plus bg times I plus af plus bh times j plus ce plus dg times k plus cf plus dh times r. This matches the matrix product. Let's try an example. M equals 2 times I plus 3 times j plus 1 times k plus 4 times r. N equals 1 times I plus 2 times j plus 3 times k plus 1 times r. So A equals 2, B equals 3, C equals 1, D equals 4, and E equals 1, F equals 2, G equals 3, H equals 1. Compute. Thus, M times N equals 11 times I plus 7 times j plus 13 times k plus 6 times r. Let's verify with matrices. M equals the matrix with 2 and 4 on the diagonal and 3 and 1 off the diagonal. N equals the matrix with 1 and 1 on the diagonal and 2 and 3 off the diagonal. This corresponds to 11 times I plus 7 times j plus 13 times k plus 6 times r, confirming our result. Quadrix multiplication isn't just different, it's faster for key matrix types. While standard methods need 8 multiplications for a generic 2x2 matrix, Quadrix slashes this to just 1 multiplication for nilpotent rich matrices, like those with zeros on the diagonal, and 2 multiplications for diagonal matrices. Even for triangular matrices, it cuts the work in half. The secret? Quadrix exploits hidden algebraic structure, like terms that square to 0, to skip redundant calculations. For unstructured matrices, it matches standard speed, but when the basis aligns, pure acceleration. In any number system, a multiplicative inverse of a number m is another number m inverse such that their product is the identity. For quadrix numbers, the identity is I plus r, since I plus r equals 1 times I plus 0 times j plus 0 times k plus 1 times r. So for a quadrix number m equals a times I plus b times j plus c times k plus d times r, we need m times m inverse equals I plus r and m inverse times m equals I plus r. Not all quadrix numbers have inverses. We'll find that m has an inverse if a certain scalar related to its coefficients is non-zero. Let's derive the inverse formula using quadrix algebra to see how this works. Let's find the inverse of m equals a times I plus b times j plus c times k plus d times r. Assume the inverse is m inverse equals x times I plus y times j plus z times k plus w times r. We need m times m inverse equals a times I plus b times j plus c times k plus d times r times x times I plus y times j plus z times k plus w times r equals I plus r. Using the multiplication formula, m times n equals ae plus bg times I plus af plus bh times j plus ce plus dg times k plus cf plus dh times r, set n equals m inverse equals x times I plus y times j plus z times k plus w times r, so e equals x, f equals y, g equals z, h equals w. The product is m times m inverse equals ax plus bz times I plus ay plus bw times j plus cx plus dz times k plus cy plus dw times r. This must equal I plus r equals 1 times I plus 0 times j plus 0 times k plus 1 times r. Equate coefficients. 1, ax plus bz equals 1, 2, ay plus bw equals 0, 3, cx plus dz equals 0, 4, cy plus dw equals 1. Let's solve these algebraically. From equation 2, ay plus bw equals 0, so ay equals minus bw implies y equals minus bw divided by a if a is not equal to 0. From equation 3, cx plus dz equals 0, so cx equals minus dz implies x equals minus dz divided by c if c is not equal to 0. Substitute x equals minus dz divided by c into equation 1, ax plus bz equals 1, a times minus dz divided by c, plus bz equals 1 implies minus a dz divided by c plus bz equals 1 implies z times b minus ad divided by c, equals 1 implies z times bc minus ad divided by c equals plus z equals c divided by bc minus ad, if bc minus ad is not equal to 0. Now, find xx equals minus dz divided by c equals minus d divided by c times c divided by bc minus ad equals minus d divided by bc minus ad equals d divided by ad minus bc. Substitute y equals minus bw divided by a into equation 4. cy plus dw equals 1, c times minus bw divided by a. Plus dw equals 1 implies minus c bw divided by a, plus dw equals 1 implies w times d minus cb divided by a, equals 1 implies w times ad minus cb divided by a equals 1. Thus, w equals a divided by ad minus cb equals a divided by ad minus bc. Find y equals minus bw divided by a equals minus b divided by a times a divided by ad minus bc equals minus b divided by ad minus bc. So the inverse is inverse equals x times I plus y times j plus g times k plus w times r equals d divided by ad times I minus b divided by ad minus bcc times j plus c divided by ad minus bc times k plus a divided by ad minus bc times r equals d times I minus b times j plus c times k plus a times r divided by ad minus bc. This assumes ad minus bc is dc is not equal to 0, and we assumed a is not equal to 0, c is not equal to 0. If a equals 0 or c equals 0, we'd need to adjust, but the denominator ad minus bc is key. We've now derived the inverse for any quadrix number, and in the process, uncovered its hidden structure. Observe how the inverse formula, m inverse equals d times I minus b times j minus c times k plus a times r, divided by ad minus bc, reveals two critical components. 1. The conjugate m bar equals d times I minus b times j minus c times k plus a times r, which strategically reorganizes the coefficients while flipping I and r. 2. The modulus m squared equals ad minus bc, acting as a scaling factor, identical to the determinant of m's 2 by 2 matrix representation. A square root of a quadrix number m equals a times I plus b times j plus c times k plus d times r is another quadrix number n equals x times I plus y times j plus z times k plus w times r, such that n squared equals m. Unlike real numbers, quadrix numbers can have multiple square roots up to 4 due to their algebraic structure. We'll derive a general formula to find all square roots, handling both general and special cases using the multiplication rules. Our goal is to find x, y, z, w such that squaring n yields m. Let's derive the formula algebraically, ensuring every step is clear. For m equals a times I plus b times j plus c times k plus d times r, we seek n equals x times I plus y times j plus z plus w times r, where n squared equals m. Using the multiplication formula, n squared equals x times I plus y times j plus z times k plus w times r, squared equals x squared plus y times z times I plus y times x plus w times j plus z times x plus w times k plus w squared plus y times z times r. Equate to m x squared plus y times z equals a, y times x plus w equals b, z times x w equals c, w squared plus y times z equals d. We'll solve these in two cases, x plus w not equal to 0 and x plus w equals 0. Case 1, x plus w not equal to 0. From the second and third equations, y equals b divided by x plus w, z equals c divided by x plus w. Compute y times z equals b divided by x plus w times c divided by x plus w equals b times c divided by x plus w squared. Substitute into the first and fourth equations, x squared plus b times c divided by x plus w squared equals a w squared plus b times c divided by x plus w squared equals d. Subtract them, x squared minus w squared equals a minus d implies x minus w times x plus w equals a minus d. Let s equal x plus w, so y equals b divided by s, z equals c divided by s, and y times z equals b times c divided by s squared. Let d equal x minus w, so d times s equals a minus d implies d equals a minus d divided by s. Solve for x and w, x equals s plus d divided by 2 equals s plus a minus d divided by s divided by 2, w equals s minus d divided by 2 equals s minus minus d divided by s divided by 2. Substitute x into the first equation, s plus a minus d divided by s divided by 2. Squared plus b times c divided by s squared equals a. Simplify s squared plus a minus d divided by s squared divided by 4 equals s to the fourth power plus 2 times a minus d times s squared plus a minus d squared divided by 4 times s squared, so s to the fourth power plus 2 times a minus d times s squared plus a minus d squared divided by 4 times s squared plus b times c divided by s squared equals a. Multiply by 4 times s squared, s to the fourth power plus 2 times a minus d times s squared plus a minus d squared plus 4 times b times c equals 4 times a times s squared. Rearrange s to the fourth power minus 4 times s squared plus 2 times a minus d times s squared plus a minus d squared plus 4 times b times c equals 0 implies s to the fourth power minus 2 times a plus d times s squared plus a minus d squared plus 4 times b times c equals 0. Let t equal s squared, t squared minus 2 times a plus d times t plus a minus d squared plus 4 times b times c equals 0. Solve t equals 2 times a plus d plus or minus square root of 4 times a plus d squared minus 4 times a minus d squared plus 4 times b times c divided by 2. Discriminant. 4 times a plus d squared minus 4 times a squared minus 2 times d, a plus d squared plus 4 times b times c equals 4 times a times d minus 4 times b times c equals 16 times a times d minus b times c. So t equals a plus d plus or minus 2 times square root of a times d minus b times c. S equals plus or minus square root of a plus d plus or minus 2 times square root of a times d minus b times c. Real solutions require a times d minus b times c greater than or equal to 0 and a plus d plus or minus 2 times square root of a times d minus b times c greater than or equal to 0. Then x equals s plus a minus d divided by s divided by 2, w equals s minus a minus d divided by s divided by 2, y equals b divided by s, z equals c divided by s. Case 2, x plus w equals 0 implies b equals c equals 0, so m equals a times I plus d times r. Then n equals x times I minus x times r, n squared equals x squared times I plus x squared times r equals a times I plus d times r. This requires a equals d, which is restrictive. Instead, try n equals plus or minus square root of a times I plus or minus square root of d times r for a d greater than or equal to 0. This gives 4 solutions for a d greater than or equal to 0. This formula yields up to 4 square roots. Let's apply it to an example. Consider m equals 4 times I plus 2 times j plus 2 times k plus r. So a equals 4, b equals 2, c equals 2, d equals 1. Since b, c not equal to 0, use case 1. Compute a times d minus b times c. A times d minus b times c equals 4 times 1 minus 2 times 2 equals 4 minus 4 equals 0. The quartic equation is s to the fourth power minus 2 times 4 plus 1 times s squared plus 4 minus 1 squared plus 4 times 2 equals s to the fourth power minus 10 times s squared plus 9 plus 16 equals s to the fourth power minus 10 times s squared plus 25 equals 0. Solve s squared minus 5 squared equals 0 implies s squared equals 5 implies s equals plus or minus square root of 5. For s equals square root of 5, x equals square root of 5 plus 4 minus 1 divided by square root of 5 divided by 2 equals square root of 5 plus 3 divided by square root of 5 divided by 2 equals 8 divided by square root of 5 divided by 2 equals 4 divided by square root of 5. W equals square root of 5 minus 3 divided by square root of 5 divided by 2 equals 2 divided by square root of 5 divided by 2 equals 1 divided by square root of 5. Y equals 2 divided by square root of 5. Z equals 2 divided by square root of 5. So n1 equals 4 divided by square root of 5 times I plus 2 divided by square root of 5 times j plus 2 divided by square root of 5 times k plus 1 divided by square root of 5 times r. For s equals minus square root of 5, x equals minus square root of 5 plus 3 divided by minus square root of 5 divided by 2 equals minus 4 divided by square root of 5. W equals minus square root of 5 minus 3 divided by minus square root of 5 divided by 2 equals minus 1 divided by square root of 5. Y equals 2 divided by minus square root of 5 equals minus 2 divided by square root of 5. Z equals 2 divided by minus square root of 5 equals minus 2 divided by square root of 5. So n2 equals minus 4 divided by square root of 5 times I minus 2 divided by square root of 5 times j minus 2 divided by square root of 5 times k minus 1 divided by square root of 5 times r. In algebra, a linear equation like a times x equals b is solved by multiplying both sides by the inverse of a. For quadrix numbers, we solve m times x equals n, where m equals a times I plus b times j plus c times k plus d times r, n equals e times I plus f times j plus times k plus h times r, and x equals x times I plus y times j plus z times k plus w times r, to find x. The solution is x equals m inverse times n, provided m has an inverse, which requires a times d minus b times c not equal to 0. We'll use quadrix multiplication and the inverse formula to compute x. Our goal is to find x algebraically, avoiding matrix methods, and verify the solution. Let's derive the method clearly. To solve m times x equals n, we need x equals m inverse times n. The inverse of m equals a times I plus b times j plus c times k plus d times r is m inverse equals d times I minus b times j minus c times k plus a times r, divided by a times d minus b times c, if a times d minus b times c is not equal to 0. Then compute x equals m inverse times n equals d times I minus b times j minus c times k plus a times r, divided by a times d minus b times c, all times e times I plus f times j plus g times k plus h times r. Use the multiplication formula. P times q equals p1 times q1 plus p2 times q3 times I plus p1 times q2 plus p2 times q4 times j plus p3 times q1 plus p4 times q3 times k plus p3 times q2 plus p4 times q4 times r, where p equals m inverse equals d divided by a times d minus b times c times I minus b divided by a times d minus b times c times j minus c divided by a times d minus b times c times k plus a divided by a times b times c times r. So p1 equals d divided by a times d minus b times c, p2 equals minus b divided by a times d minus b times c, p3 equals minus c divided by a times d minus b times c, p4 equals a divided by a times d minus b times c, and q equals n equals e times I plus f times j plus g times k plus h times r, so q1 equals e, q2 equals f, q3 equals g, q4 equals h. Calculate x equals times I plus y times j plus g plus z times k plus w times r. For I term, x equals p1 times q1 plus p2 times q3 equals d times e, divided by a times d minus b times c plus minus b times g, divided by a times d minus b times c equals d times e minus b times g, divided by a times d minus b times c. For j term, y equals p1 times q2 plus p2 times q4 equals d times f, divided by a times d minus b times c plus minus b times h, divided by a times d minus b times c equals d times f minus b times h, divided by a times d minus b times c. For k term, z equals p3 times q1 plus p4 times q3 equals minus c times e, divided by a times d minus b times c, plus a times g divided by a times d minus b times c equals a times g minus c times e, divided by a times d minus b times c. For our term, w equals p3 times q2 plus p4 times q4 equals minus c times f, divided by a times d minus b times c plus a times h, divided by a times d minus b times c equals a times h minus c times f, divided by a times d minus b times c. So x equals d times e minus b times g times I plus d times f minus b times h times j plus a times g minus c times e times k plus a times h minus c times f times r, all divided by a times d minus b times c. This solution assumes a times d minus b times c is not equal to 0. If a times d minus b times c equals 0, m has no inverse, and we'd need to check if solutions exist, similar to singular matrix equations. Complex numbers form a specific algebraic structure that can be embedded within the broader system of quadrix numbers through a precise mapping that preserves their core operations. This mapping, known as an injective ring homomorphism, ensures that the addition and multiplication of complex numbers translate directly into corresponding operations in the quadrix system, maintaining their commutative nature. Essentially, every complex number has a unique quadrix counterpart, allowing complex arithmetic to be faithfully replicated within a subset of the quadrix framework, making complex numbers a special, well-behaved part of the quadrix algebra. However, this relationship is not a complete equivalence, as quadrix numbers possess a richer structure that complex numbers lack. While complex numbers operate within a commutative field, quadrix numbers form a non-commutative ring, meaning some quadrix elements exhibit multiplication behaviors, like non-commutative products, that have no counterpart in the complex system. This makes the embedding one-directional. All complex numbers can be represented as quadrix numbers, but many quadrix numbers, particularly those with non-commutative properties, cannot be reduced to complex numbers, highlighting the greater generality of the quadrix algebraic system.